Okay, we're going to get into some applications of the dot and cross product, and it's really important that we try to keep in our minds what it is we're actually doing. So we're starting slowly, but try not to fall into an algorithm and try to think about what's actually happening here. So first up, the projection of an object onto a line or a plane is formed by dropping a perpendicular from each point on the object to the line or plane. So a shadow is a really good example of a projection onto a plane. And the projection of one vector onto another can be shown as follows. So let's say that this is vector u and this is vector v. And so I want to know what the projection of u onto v is. And so I can write that projection of a big U onto v. So I'm going to take u and I'm going to think about what would its shadow look like if it was projected onto v. And it's going to create a shadow all along this portion of v. So this is the projection of u onto v. And it can go the other way too. So let's say this is u and this is v. And again, I'm just going to think about where does that shadow exist. And so here is the projection of u onto v. Okay, so we can talk about this from an algebraic term too. So the projection of vector u, these are all vector arrows, onto v is actually the dot product of u dot v times the vector v divided by the absolute value of vector v squared. And then the magnitude of that is just the dot product of u dot v all divided by just the magnitude of v. So let's try some examples. So I want to find the projection of vector 2, 2 on the vector 3, 0. And so I might actually even start by drawing a axes and thinking about what this looks like. So 2, 2 is going to be somewhere about here. Here's vector 2, 2. And 3, 0 is going to be something like that. And so I'm looking for this projection right here. And so maybe from this diagram you can already guess what's going to happen, but let's just work it out. So projection of u onto v is u dot v all over v squared times vector v. So let's find u dot v. So I have the point 2, 2, and I have the point 3, 0. And 2 times 2 is 6, and 2 times 0 is 0. So that'll be 6 plus 0 on the top. And on the bottom, I have the absolute value of vector v. So I'm going to take 3 squared, which is 9, and take the square root of that. So the root of 9 will be the absolute value of v, and that's all squared. And this is all multiplied by the vector v, because that's the direction that I'm going. Okay, to simplify this, I'm going to have 6 over 9 as a scalar, and that can be reduced to 2/3 over multiplied by that. I'm going to multiply this in, distribute it. Okay, so that's going to give me the vector 2, 0. And if you look at our resultant vector, well, that makes sense because the point 2, 2, if you were to drop it down, it only goes 2 in the x direction, so it does make sense that this point here is 2, 0. Okay, the question also wants to know the magnitude. So the magnitude of projection u onto v is u dot v all over the magnitude of v. And I already have that value here. There's my dot product there. So I'm just going to move that over there. And I already have the magnitude of b as well, so that's 9. And so that's going to be 6 over 3. So the magnitude of this vector is 2. And that also makes sense based on my diagram. Let's try an example in 3 dimensions. So I'm going to find the projection of vector u onto v. First thing I need to do is find the dot product. Then I need to find the magnitude of v. Then I need to multiply this all by the vector v. Okay, so first up, dot product, I'm going to go 3 times -1, -3. 2 times 5, 10. -1 times 4, -4. Okay, now I'm going to take this vector v and find the magnitude of it. I'm going to have 1 plus 25 plus 16, which is 42. And then I'm going to write vector v here as well. That's the direction that my shadow is going. Okay. -3 plus 10 minus 4 is 3. The root of 42 squared is 42. And there's the direction of my vector. This can be reduced. And we can multiply this in. You will see both types of answers in the back, whether or not there is a scalar value of k or it's been multiplied in. Okay, let's find the magnitude of the projection. So I know where it's going, of u onto v. Okay, so that's the magnitude of the dot product, all divided by the magnitude of vector v. So the magnitude, so my dot product was 3, and vector v is root 42. Okay, so let's start looking at some applications of this. So the area of a parallelogram is the base multiplied by the height. And so I can call this vector v here, and this vector u. And if I drop a perpendicular here, that's how I would find height. And then I'm going to have some angle there. Okay, so if I wanted to figure out this value, just thinking about what I know outside of this class from before this lesson, before this class, then I would say that sine of theta is h over vector v. And I can rearrange this to solve for h. So I can say that h is vector v times sine theta. Now, because I am not interested in the direction of vector v, but the magnitude of vector v, I'm going to change that to a magnitude of vector v. Okay. And the area of a parallelogram is the base times the height. Well, the base, in this case, is vector u. So the base is vector u. So I'm going to substitute base for vector u, and I don't care about its direction. I'm only interested in its magnitude for area. And for h, I'm going to substitute my new value for h. Now this looks very familiar. We've seen this before. So this is the cross product of u cross v. So I can replace this. So I can say a is actually the magnitude of u cross v in order to find the area of a parallelogram. And the same thing is going to happen if I have a triangle. So again, let's call this v and this u. And I can work through the exact same thing, but I'm going to come to the same conclusion that the base times the height is actually u cross v. And now in this case, I'm going to just divide that by 2. Okay, let's try an example. So let's determine the area of a parallelogram that has sides defined by these vectors. And then I also want to figure out whether or not this parallelogram is a rectangle or not. So I know that the area is u cross v. And so I'm going to do my cross product. Okay, so I'm gonna write it over here. And 2, 4, -1. Get rid of these guys. Okay, I've got 1 take away 8. I've got 4 take away -3. I've got 12 take away -2. So I'm going to have -7, +7, 14 is the cross product. And so now I'm going to find the absolute value. So I need to take the square root of 49 plus 49 plus 14 squared is 196. And the root of that, add that all up, is 234. So the area of this parallelogram is 234. So the second part of that question asks me, is this a rectangle? So it's going to be a rectangle if I have a 90-degree corner. And if I have a 90-degree corner, then the dot product of u dot v is going to be 0. And that's going to mean that u and v are perpendicular. Okay, so let's take u dot v. Okay, so I have 2 times 3, which is 6, minus plus 4 times -1, which is -4, plus 2 times -1, which is -2. And this does equal 0. So therefore, this is a rectangle because u dot v equals 0. So this is a 90-degree corner. Okay, let's try one more example. All right, so here is a parallelogram, and I want to find the area. So we're going to take vector u and vector v, and we're going to do u cross v. Okay, first up, I've got -6, take away -5. I have -10, take away 2. I have -1, take away 6. So u cross v is the vector -11. Oh, this should be, I missed a negative there. -8 should be positive, and -7. Okay, so my area is the absolute value of u cross v. So now I'm going to find the absolute value of this. I'm going to square all of these things. 121 plus 64 plus 49. This is going to be 234. Oh, and I see I made a translation error up here. So just going back, this sums up to root 294. That was my bad. I was looking at my answer key here. Okay, last up, maybe I'm interested to know, is this a rectangle? Okay, so let's find u dot v. Okay, so I'm going to have 2 times -1, -2, plus 1 times 3, plus 2 times negative 2 times negative 5, which is